Good morning, chemistry students. Here are your Chapter 6, Day 2 notes. This is going to cover all of Chapter 6, Section 2. And in this section, we're starting to talk about, remember in previously in Chapter 6, we sort of did an overview of molecular compounds with covalent bonds and made of two nonmetals, and ionic compounds with ionic bonds and made of metals and nonmetals or polyatomic ions. Today, we are kind of talking about how we represent these chemical compounds. So we're going to talk about the formulas for these. So section 6.2 is titled Representing Chemical Compounds, and we're going to start by talking about chemical formulas. The definition of a chemical formula is that a chemical formula shows the kinds and numbers of atoms in the smallest representative unit of a substance. So, one of the things about chemical formula is this idea that it is a generic term. I can refer to the formula of any kind of compound as a chemical formula. When we're talking about chemical formulas, when we're talking about something that is monatomic, the chemical formula will be just the element symbol. For example, if we're talking about neon, the chemical formula is just Ne, because remember, neon's a noble gas. It doesn't get involved in forming chemical compounds, and therefore it's a monatomic element. We also have substances that are diatomic. Diatomic means it's made of two atoms. And specifically with the diatomics, you have 7 that you are memorizing as part of your polyatomic ions to memorize. Again, these are diatomic molecules, and these are elements that never exist as a single monatomic atom. If they are pure and by themselves, they always exist as diatomic molecules. And there are 7 of them. Okay. And they were H2, O2, F2, Br2, I2, N2, and Cl2. Hofbrinkel, okay, or Brinkel-Hof. So again, in the classroom, there are a couple posters with these. When you get into Google Classroom, the banner that you should see is these 7 diatomic molecules. This will be important when we move into Chemistry B and we start to talk about chemical equations and such, because if we ever have bromine all by itself reacting, it'll always be Br2. And as I already mentioned about chemical formulas, a chemical formula is a generic term. It works for both molecular and ionic compounds. So we can call the chemical formula of a molecular compound a chemical formula. We also can call the formula of an ionic compound a chemical formula. So chemical formula you can kind of think of as like an umbrella or a generic way to refer to a formula. So now that we've talked about kind of what these are generically, we're also going to talk about the fact that there are actually specific names for the chemical formulas of molecular and ionic compounds. And we've touched on this before, but we're going to kind of specifically talk about it now. So we're going to start by talking about molecular formulas, which means we're going to be talking about molecular compounds, which means we're talking about covalent bonds. So the definition of a molecular formula is that it is the chemical formula of a molecular compound. So this is specific for a molecular compound. I cannot refer to the chemical formula of an ionic compound as a molecular formula. So if we say, write the molecular formula for water, what that means is that we've communicated a little bit more information about the compound water. By referring to the formula of water as a molecular formula, that means that it's a molecular compound. A molecular formula still shows the kinds and numbers of atoms present. And this time, instead of saying in a representative unit, we're going to get more specific about what that representative unit is. In a molecule of a compound. So again, the smallest piece of a molecular compound is a molecule. So a molecular formula shows the kinds and numbers of atoms present in a molecule of a compound. A subscript tells the number of atoms of the element. We don't write ones. So when there is not a number written, okay, it's a 1. Okay. The problem with molecular formulas is that a molecular formula doesn't tell how the atoms are connected to one another. So some examples of molecular formulas are H2O, carbon dioxide, C2H6. Remember, what makes something a molecular compound is that it's made of 2 non-metals. Okay, so again, water made of 2 nonmetals, carbon dioxide made of 2 nonmetals, C2H6 made of 2 nonmetals. Therefore, these are molecular compounds. Therefore, these formulas are molecular formulas. Remember, it would not be wrong to refer to these also as chemical formulas because chemical formula is generic. But by calling them a molecular formula, again, we're communicating a little bit more information about the compound. We're saying this is a compound that is a molecular compound. It's going to have covalent bonds in it, and it's going to be made of nonmetals. So again, molecular formula is more specific then chemical formula. Formula units. Remember when we talked about ionic compounds, we said that ionic compounds are arranged in orderly patterns. We talked about the fact that they had those repeating three-dimensional patterns. In fact, many ionic compounds are crystals. And because of that, therefore, there are no separate units. Really, ionic compounds are an array of ions. However, that's not particularly useful to us when we're trying to write a chemical equation and balance a chemical equation. So, we always, when we're talking about ionic compounds, even though they exist as these three-dimensional repeating patterns that oftentimes form crystals, we always talk about what's called a formula unit, which is the lowest whole number ratio of ions in an ionic compound. Now remember, an ionic compound is made of ions, a cation, a positively charged ion, and an anion, a negatively charged ion. Although ionic compounds are made of ions, the charges of the ions aren't written in the chemical formula. Now, I will never count it wrong if you have your charges in there, but if you're going to bother to rewrite the chemical formula for an ionic compound, realistically, you should leave the charges out. Specifically, we can also say that a formula unit is the chemical formula for an ionic compound. Remember that ionic compounds had to be neutral. So, for example, when we talk about combining a sodium ion and a chloride ion, we have to combine them so that overall there's zero charge. The total positive charge has to equal the total negative charge. Since sodium has a +1 charge and chloride has a -1 charge, I can combine them in a 1-to-1 ratio. So my formula unit would be NaCl. If you would take a moment to practice writing the formula unit for ion and a chloride ion, as well as a aluminum ion and chloride ion. Remember that overall we have to have a zero charge, so we have to combine so that our total positive charge equals our total negative charge. So for magnesium and chlorine, magnesium has a +2 charge, chloride has a -1, so I'm going to need 2 chlorides to combine with that 1 magnesium to overall have a negative charge. So my formula would be MgCl2. When I'm talking about aluminum ion and chloride, because aluminum has a +3 charge, it's going to take 3 chloride ions, and so my formula is going to be AlCl3. Again, we're going to get more practice doing this later, so if you're still kind of feeling a little overwhelmed by this, it's okay, right? We are going to continue to do this, and we're going to practice this some more. So, again, sorry, before we move on, remember, calling something a formula unit means we're just communicating a little bit more information. It's still the chemical formula, but we're specifically saying it's the chemical formula of an ionic compound. So again, it would not be wrong to say MgCl2 or AlCl3, that those are chemical formulas. That's perfectly fine. However, by calling them a formula unit, we're communicating that little tiny bit more information about the fact that these are not just some generic kind of compound. These specifically are ionic compounds because we've called them formula units. So that's what's nice about the terms formula unit and molecular formula. They are specific to a specific type of compound, and they communicate that little bit more information. All right, the last thing in this section is about the laws of definite and multiple proportions. We don't spend a lot of time on this, but it is nice to know what these are. So the law of definite proportions says that in samples of any chemical compound, the masses of elements are always in the same proportions. Another way to kind of look at this then is saying that for a compound to be the same compound, no matter where it is in the world, the masses of elements are always in the same proportion. So what this is saying is, like, for example, water. The mass of hydrogen to oxygen in water is the same in all water molecules. What that also means is that if I have different proportions but the same elements, I have a different compound. Again, because if it was the same compound, the proportions would be the same. And this really kind of goes back to John Dalton again, one of those scientists we talked about in Chapter 5. Dalton postulated, which means he kind of guessed or hypothesized, that atoms combine in simple whole number ratios. And he said that if the ratio of the atoms of each element in a compound is fixed or always the same, then it follows that the ratio of their masses is also fixed or always the same. So again, kind of what he was saying was he knew at that point that a hydrogen atom always had the same mass and an oxygen atom always had the same mass. So he said if water's always H2O and the mass of hydrogen or oxygen doesn't change, then the ratio of their masses for all water should be the same. So to take a look at an example of this, peroxide is H2O2. So when you look at your periodic table, and again, we're going to talk about this in Chemistry B, but as a little preview, on your periodic table, there's those average atomic masses, which are the masses of the elements. So when I look at oxygen, its number is about 16. And notice I have two oxygens here. So I'm going to say that the mass of oxygen is 32 grams of oxygen. That comes from two oxygens, each at 16. So 2 times 16. Okay. For hydrogen, when I look at hydrogen's atomic mass on the periodic table, it's 1. And there are two hydrogens here, so that makes 2 grams of hydrogen. Now, that's not the lowest whole number ratio, so I'm going to make it the lowest whole number ratio, right, which would make it 16 grams of oxygen to 1 gram of hydrogen. What this is saying is that in all hydrogen peroxide, anywhere you find it in the world, the mass of oxygen to hydrogen is 16 to 1. Now, let's compare that to water, right, which is H2O. So now oxygen has a mass of 16, but there's only one of it, so that's 16 grams of oxygen. Hydrogen is still a mass of 1, but there's 2 of them, so that's 2 grams of hydrogen. Again, that's not my lowest whole number ratio. My lowest whole number ratio is 8 to 1. So notice my ratio is different, right? And that's what we were just saying, is that different proportions but the same elements is a different compound. Okay? That's what we're showing here, right? Different proportions but the same elements, we have different compounds. The law of multiple proportions says when two elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in a ratio of small whole numbers. So when two elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in a ratio of small whole numbers. So we're going to take a look at that back on what we just looked at here, right? So that was the law of multiple proportions. Notice I have the same amount of hydrogen, right? And that's what it's talking about here. It says the same mass of the other element. So what's staying the same here is my hydrogen. So what I want to look at is the ratio of 16 grams of oxygen to 8 grams of oxygen. Notice that's a 2 to 1 ratio. That's saying that peroxide has twice as much oxygen as water does. And we see that that's true in our chemical formula as well. So that's all the law of multiple proportions is saying. Your homework tonight is pretty short. It's page 142, question number 12. Have a good day. I'll talk to you tomorrow.